Okay, we're going over section 4.6. This is the second half of chapter 4. So could we split it up? And here's the title of section 4.6, Perform Operation with Complex Numbers. So we're going to learn about some numbers that are new to your world, which is pretty neat. First one, imaginary unit, I. So somebody came along and defined I to be the square root of -1. And you should be saying, hey, I've been told over and over again, you can't take the square root of -1. And so these are imaginary numbers. They don't really exist. So it's a bit uncomfortable, but it allows us to do certain problems. It's kind of a breakthrough, if you will. Complex number. So a complex number is written in the form a plus bi. And a and b are both numbers, and the I part is the imaginary part. So here's an example. 2 plus 3i. That is called a complex number. The 2 is a real number 2, just like you've always worked with. And 3i, this is an imaginary number. This number actually does not exist. Again, feels like we're talking crazy, but it works. So if 2 were to be 0 here, we'd call this strictly an imaginary number. Right? And if 3 were to be 0 here, we'd call 2 just a real number. Complex conjugates. So the 2 plus 3i, its conjugate is 2 minus 3i. We've already done conjugates, but now it's called a complex conjugate because there's an imaginary part. The complex plane, let me read it to you, and it'll make so much more sense when we get to this example later on in the lecture, is a coordinate plane where each point AB represents a complex number, a plus bi. And the horizontal axis we'll call the real axis, and the vertical axis will become the imaginary. The absolute value of a complex number is really the distance from the origin to a point. Again, let's kind of put these two guys aside till we get to their example. So here we go. The square root. This is a big one now. When you get an example, I'll read the property. If r is a positive real number, then the square root of -r becomes I root r. So here's our example. Check it out. Square root of -3. Again, you over and over have been told that's impossible. It's not allowed. But what we get to do now is we say, hey, the negative becomes this I. And I would highly encourage you to write I with that little tail, right? We don't want to, if you just make it like this and you can't see this dot, all of a sudden it looks like a 1. So give I a little tail and you'll never confuse it. And so again, this was a big move for us in the math world to be able to, define or just to go one step further than saying it's not possible. We say now it is, but we call it an imaginary number. Pretty neat. If I squared that number, right, we'd get I squared times 3, and I squared is actually equal to -1 times 3, and this would get you back to -3. So again, big property, maybe write that in your notes, that I squared is equal to -1. And that's pretty amazing, right? You get this imaginary number I, when you square it, you get a real number, -1. Let's walk through this example. So this, again, solving quadratic equations. So it looks just like an equation out of section 4 or 5. But as we go through the steps, you see right away that you're heading towards a negative square root, right? So first we were going to subtract 15 from both sides, and then we would divide by 2. So now you're geared up, right? You got x squared equal to some number. You're going to take square root of both sides. And we're into this world where, again, the square root of -25 is not possible. But now we're allowed to write this as plus or minus I, right? This is an I. Their script isn't great. This is an I sitting right there. And the square root of 25 is actually 5. So you're going to get two answers. 5i, an imaginary number, not a real solution, and -5i, which is another solution, both imaginary. And interestingly enough, this quadratic would not cross the x-axis, so that's why we're getting imaginary roots. We'll talk about that later. Hey, why don't you go ahead and try to solve this? Again, I'm just telling you straight up, you're going to get an I answer. But see if you can't walk through the steps. Hit pause, and when you're done, hit play, and you'll see the solution. Here you go. So the answer is plus or minus 2I root 3. Here are the steps I took. So I subtracted 13 from both sides, divided by 3, took the square root of both sides, plus minus. Please don't forget the plus minus. And now we're into this negative 12. The negative turns into I, and don't forget 12 is the same as square root of 4 times the square root of 3, which would give you 2 root 3. I hope you got that answer. We'll practice more in class. So complex numbers, what can we do with them? Well, we can add complex numbers. And when we add complex numbers, we add their real parts. Make sure I got this right. We add their real parts and their imaginary parts. So let's put the word real here. Right? So we would add A plus C separately, and then we would add their imaginary. Sorry for the poor penmanship. Where you can see that we'll take the B term in front of I and the D coefficient and add them together. And we'll do that separately. Nice. Subtracting, we just got to be careful because we're going to subtract both parts. So again, this negative gets distributed to both C and D. Let's go ahead and look at two examples. So first, let's talk about subtracting. So when we subtract two complex numbers, again, we're going to say 6 minus 4 and 3 plus 1. Again, this negative will distribute. I love drawing my arrows, personally. I'm always worried that I'm going to miss that. So here you can see it's 6 minus 4 and 3 minus minus, or plus 1. And your final answer should be back in standard form. Right? Standard form, just so you're aware, standard form is always A plus BI. Two parts, a real part and an imaginary part. Adding complex numbers is nothing quite as nice, right? It's just 2 plus 7 and 5 minus 2, and you've got your complex number, again, in standard form. Nice job. Multiplying complex numbers. All right, this gets a little more exciting. So if you kind of look, this has that same look as what you were expanding intercept form, and we FOIL here. That's our first step. So multiply using FOIL. Everybody gets multiplied. 2 times negative 5 is negative 10. 2 times 2i is 4i. I times negative 5, negative 5i. And finally, I times 2i is 2i squared. So we're not done. Hopefully you can see here I've got like terms. These guys are like terms. And then I don't know if you remember in our notes, we said that I squared was equal to negative 1. And we're going to use that. We're going to replace the I squared with negative 1. Let's see our steps. Right? So we combined like terms. 4i minus 5i is negative 1i. And then notice that the I squared turns, sorry about the line, I mean do that, to negative 1. And so 2 times negative 1 is actually negative 2. And then, hey, wait a sec, we've got like terms here. And final answer is negative 12 minus I. And again, that's in standard form. Negative 12 is the real part, and negative 1i is the imaginary part. So here we go, hardest one, dividing complex numbers. So here you go, you have a complex number 6 plus 4i and divide it by 2 plus I. How do we do that? Well, the trick here is to multiply by the conjugate. So the denominator, the conjugate of the denominator. And our denominator is 2 plus I. So we multiply top and bottom. And you should be saying, well, are you allowed to do that? Well, if you notice, 2 minus I over 2 minus I is another way of writing 1. And we can certainly multiply anything by 1 and not change its value. So you should be kind of sitting there going, oh my gosh, now I got to FOIL the top and the bottom. And the top is quite a bit of foiling, right? We're going to FOIL, there's the top foiled out. 6 times 2 is 12. 6 times negative I is negative 6i. 4i times 2 is 8i. And 4i times negative I is negative 4i squared. The bottom, and this is quite nice, and this is why the conjugate works. If you notice, 2 times 2 is 4. Then you've got what's going on here in the middle term. You've got negative 2i plus 2i. And these guys will cancel. And that's really why we multiply by the conjugate. So if we simplify, they did quite a bit of simplifying here. First, they combined the middle terms, right? Then they said I squared is the same as negative 1. So that would become negative 4 times negative 1 is positive 4. 4 plus 12 is 16. You can see how that went. And then the bottom here, these middle terms canceled. 4 minus I squared is the same as 4 plus 1. Do you agree? I squared is negative 1. Negative 1 times negative is positive. Positive 1 plus 4 is 5. So you're not really done here because you're still not in standard form. And notice how they broke this up. They said 16 divided by 5, the real part. 2i divided by 5, the imaginary part. You need to try. So why don't you hit pause? You're subtracting, you're multiplying, you're dividing, you're adding. Again, really put your emphasis on problem 4, and we're going to practice this a lot. Problem 4, you will multiply by the conjugate. The conjugate, can you see it? Well, hit pause and see how you do. And there are the answers. So answers are in red. Again, subtracting, make sure you distributed the negative. Multiplying, again, nice distribution here. Don't forget to get rid of I squared. I squared is the same as negative 1. Here's the conjugate, 3 minus I. When you FOIL, the top should have looked like this, and the bottom, I don't even write the middle term anymore. I know that the 3i and the negative 3i will cancel, so I stop writing it after a while. And then you should clean up to here, and then, again, you have to go that final step to go to standard form where it's 20 divided by 10 and minus 20 I divided by 10, and your final answer is that. If you got this answer, well done. We'll practice more in class. Last bit here, and kind of a nice part, we have what's called the complex plane. It's very different than the Cartesian coordinate, plane that you've worked with. The x-axis is now the real axis, and the y-axis is the imaginary. So my first point, I'm going to graph this complex number, 4 plus 3i. So I would go over 4 units in the real, 3 units in the imaginary, and that's point A. I'm going to label it as such. The point B is going to be negative 5 comma negative 4i. So I'd go negative 5 on the real axis, down 4 on the y-axis. I'd be down here, B. And I also want to bring up the absolute value. So here, if I wanted to figure out the absolute value, what that means physically is what is the distance from the origin to this location. And we end up making a right triangle and just using Pythag. We say this is 4, this is 3, so this would be a 3, 4, 5 triangle. So the absolute value of that complex number is 5. That's what we're doing here. So the absolute value of a complex number, a plus bi, is denoted. We use this nice absolute value of z. It is a non-negative real number. It's always just the distance from the origin to the plotted point. And we use Pythag to solve. Let me do one example here. So this would just simply be, if I wanted to figure out this distance, would be 6 squared plus 8 squared. And that you can see is 36 plus 64, which is square root of 100, and it's 10. So again, if I were to graph this guy, 6 over on the real axis, down 8 on the imaginary, I would be 10 units from the origin. This one's nice. This is just 0 squared plus 6 squared. And you can see that's going to be square root of 36, or just 6. Once you go ahead and try to plot these and also find the absolute value, go ahead and hit pause. And here are your answers. So negative 4i is just, it's on the imaginary axis, straight down 4. Kind of don't even need to do Pythag, right? You're 4 clicks from the origin. These guys are a little harder, like the 2 plus 3i. Basically, you're trying to find that distance. And again, if you made a right triangle, this would be 2, this is 3. You'd square both numbers, take the square root, and you'd get root 13. Nice job. See you in class.